All right, let's just dive right into this explainer where we are going to completely demystify the modern natural language processing landscape. We're taking a journey from those high-level, easy-to-use APIs right down into the absolute nuts and bolts of deep learning transformers. If you've ever found yourself wondering what exactly is happening under the hood of today's incredibly powerful language models, well, you are definitely in the right place. So, we're going to investigate exactly how computers manage to parse the messy, incredibly nuanced world of human language using today's open-source tools. And to be clear, we aren't just talking about basic keyword matching here. Oh no, we're talking about sophisticated algorithms that can actually parse context, understand tone, and even generate entirely novel sentences that literally sound like they were written by a real human being.
To get us there, here is our roadmap. Number 1. Hugging Face Inference Pipelines. 2. Open Source Sentiment Analysis. 3. Building a BART Summarizer. 4. The Limits of Ruse Scores. And finally, number 5. NLP for Code Switching.
Okay, Section 1. Hugging Face Inference Pipelines. Let's start with the big picture and look at how developers actually access and implement these powerful models in the real world today.
Think of the Hugging Face pipeline as the ultimate gateway. It's just a brilliant tool that essentially abstracts away all of the intense, headache-inducing complexity of machine learning into a single, highly adaptable API call. Whether you're doing automatic speech recognition and need to throw some timestamps onto your meeting notes, or you're generating text from scratch, you just pass your data into this generic pipeline class or a task-specific one, and the API totally handles the heavy lifting for you.
And what's really amazing is how flexible this pipeline is under the hood. It allows developers to accelerate inference and save precious memory by seamlessly shifting across different hardware environments. So whether you are running on a heavy-duty GPU, optimizing for Apple Silicon, or using half-precision weights, the API adapts automatically. This is a total game changer because let's face it, in modern NLP, memory is literally your biggest bottleneck. Moving right along to Section 2, Open Source Sentiment Analysis. Let's drop one level deeper and see how these pipelines are practically applied to real-world business use cases. Basically, every single sentiment analysis workflow breaks down into 3 pretty succinct steps. First, acquiring your messy data, stuff like social media posts or customer reviews. Second, selecting your analytical engine. And third, the actual analysis, where you process that text to classify it as positive, negative, or neutral. Now, open-source platforms absolutely shine in this third step, giving you the robust classifiers and algorithms you need to process all that text at scale. But the really crucial point here is the massive divide at Step 2. Developers hit a fork in the road and have to choose between 2 completely different approaches. On one hand, you've got lexicon tools like Vader or TextBlob. These basically score text against a predefined word dictionary. They're incredibly fast, super light on memory, and just great for short, informal social media posts. But on the other hand, you have transformer models like Flare or the ones hosted on Hugging Face. These actually read words in context, meaning they can handle tricky stuff like sarcasm, negation, and mixed opinions. The trade-off, though, they require massive compute power and generally need a dedicated GPU to run efficiently. Otherwise, you're probably going to end up melting your laptop.
All right, Section 3, Building a BART Summarizer. Let's really open up the hood now and dive into the micro level by looking at a custom-built model that was fine-tuned on nearly 38,000 professionally written news articles.
Now, to understand why this specific BART model is so impressive, you kind of have to look at the alternatives. Traditional extractive models, they just copy and paste the most important sentences directly from a source article. Sure, it's safe, but it often lacks coherence and flow. This BART model, however, performs abstractive summarization. That means it actually generates fluent, entirely novel text, much like a human writer would, by deeply understanding the content and then rephrasing it concisely. But achieving that human-like fluency, yeah, that requires some serious engine power. Specifically, 406 million trainable parameters. During the fine-tuning process for this model over 3 epochs, this created some incredibly intense memory challenges. Just to give you an idea, a batch size of only 16 sequences was enough to completely overflow a 16GB Tesla T4 GPU. The developers literally had to cut the batch size in half and truncate the input articles to 512 tokens just to get the model to fit into memory without crashing the whole system.
So once you actually manage to get the model trained, how does it choose the right words for the summary? Well, to squeeze the absolute best results out of all those parameters, the system completely abandons a short-sighted method called greedy decoding. Greedy decoding just blindly picks the highest probability word at each step, which often leads to globally poor, clunky summaries.
Instead, our model uses a technique called beam search. It explores multiple candidate sequences, in this specific case, 6 different beams at once, to find a summary that makes the most sense overall, even if it takes a little bit longer to compute.
And honestly, this quote right here brilliantly illustrates exactly why those advanced decoding strategies are so necessary. Without proper decoding and a setting called a repetitive penalty, an autoregressive model will often just get stuck in local minima. It'll start producing these looping, totally incoherent word salads, acting like a confused robot stuck on repeat. My friends are cool, but they eat too many carbs. My friends are cool. Setting a repetition penalty of 1.2 essentially tells the model to artificially reduce the probability of words it has already used, which forces it to generate diverse, natural-sounding sentences instead.
Which brings us to Section 4, the limits of Rouge scores. This is a big one. If our model is generating totally novel text, how do we actually measure if the summary is any good? Typically, the industry standard is to evaluate it using ROGE metrics. Rouge measures the strict word-for-word overlap between the text the machine generated and a human-written reference summary. For example, in this BART project, the model achieved a Rouge 1 score of 21.88%, meaning about 22% of the single words in the generated summary exactly match the human reference. It also tracked Rouge 2, which sits at 12.90% for 2-word phrases, and Rouge L at 21.88% to check the longest common subsequence for sentence structure. But guys, we need a massive reality check right here. Rouge scores have some glaring, severe limitations. Because they only look at exact word matches, they completely ignore semantic similarity. If the human reference says company and the model writes firm, Rouge scores that as a flat 0. And worse, it doesn't penalize factual errors at all. A model could generate a summary saying a company's revenue grew 10% when the article actually said it declined 10%. But because it used the right vocabulary words, it would still receive a highly respectable Rouge score even though the summary is factually disastrous.
All right, our final section, number 5, NLP for code switching. Let's see how all this foundation builds into the absolute cutting-edge frontier of NLP, understanding mixed languages.
We are now seeing incredibly specialized models being deployed out in the wild, like AnE-NER, which stands for Any English Code Switching Named Entity Recognition. Now, code switching is when humans naturally mix languages in a single sentence. It's highly common in global communication, but historically, it has been an absolute nightmare for machines to parse. This model, though, classifies named entities at a microscopic word-by-word token level. It identifies whether a word is inside or outside a named entity, even when the languages are blending together in real time. If you are building a global customer service bot, this level of microscopic understanding is just absolute magic. So as these open source tools just keep pushing the boundaries of how machines parse human nuance, from massive 406 million parameter summarizers to token-level code switching identifiers, it leaves us with a pretty vital question to ponder. As our evaluation metrics clearly lag behind our actual models, are our current systems genuinely measuring true semantic understanding, or have we just brilliantly engineered the illusion of it? Thanks so much for exploring the engine room with us today. Until next time.